All right, welcome to Thermodynamics. I had a homework-related question related to me, and remind me again, that was
37. It's finding the temperature and specific volume.
okay, and that's chapter 4.
Yeah. No, chapter 5.
Chapter 5. So let's look at that. So 537. Initial. What it says is initially what we know is we have a piston cylinder device, steam at pressure P1 200 kilopascals. It's 200 degrees C, and 0.4 cubic meters. And heat is slowly transferred to the steam, causing the pressure and volume to rise to 250 kilopascals. So P2 is 250 kilopascals. And P2 is 0.6 meters cubed. Fine. I don't know I'll work the entire problem here because this find work, steam, and Q transferred. So that's basically what we're looking at. So there's a spring here. What we don't know is the mass, and the mass of stuff involved is going to give us the total scale for it. We can find individual properties and work it from there. But basically, what is Q? Q is going to be total Q added is going to be H2 minus H1, which is, and if the mass isn't changing, it's the same before as it is after, then what can we say? It's the mass 2 H2 minus mass 1 H1, but the mass doesn't change, so we can just say whatever the mass is in there, we can find that from our initial condition. And then, oops, I'm differentiating big H's and little h's for whether it's per unit mass or whether it's in total. In your lab or in your test coming up, there'll be a question that says, what is the total energy? And that's not the little h, that's the big H. I'll go over what's on test here shortly also when we're done talking about this. So use the initial conditions to find what the mass is. Yeah, and what they gave us was the original total volume. So the specific volume equals, well, specific volume is a property at P1 is 200 kilopascals. T1 is 200 degrees C. Now we need to look at tables to find out what specific volume is, because this was a total. So,
It's 1.08049.
okay. And just to show how we find where that's coming from, 200 kilopascals and 200 degrees C is going to define everything else. It's not in range yet. At 200 degrees C, we would need 1,500 kilopascals to keep it together, to keep it in saturation. Or to look at it another way, at 200 kilopascals, we only need 120 degrees for saturation, which means if we look at the pressure and look at that temperature, say, wow, we're above that temperature. So we must be in superheat table. Probably the best way to do that is look at pressures and see what the temperature is and see if your temperature is above, below, or equal to that. So at 200 kilopascals, which is 0.2 megapascals, that's this one, and we're at 200, so we're all vapor because we went above that thing, so we got a 1.08049. That first column is specific volume. So 1.08049 meters cubed per kilogram. Now I can figure out, from that I can figure out what mass I'm dealing with. And they give us total volumes. Oops. There we go. So, specific volume, just looking at units, is going to be total volume over mass, which means if I solve that for mass, I could say that my mass is going to equal total volume divided by specific volume. In this case, it's 0.4 cubic meters divided by 1.08049 meter cubed per kilogram. And remember always this, watch your units. I was pointing out to somebody that following your unit, sometimes you can, even if you don't know what the formula is supposed to be, if you know what your outcome is supposed to be and know what you're starting with, and you've watched the units and how they cancel, sometimes you can get the answer and then back into the formula and say, oh yeah, I recognize that formula, I just didn't know which one to use. So the units tell the tale. Don't ignore, if something's squared, just don't sort of, there's a reason why it's there. So that gets us units of kilograms, and it's going to be something like 0.4 kilograms.
1.372.
Thank you. And that's state 1. So that's M1, but M1 we still have 0.3702 kilograms. And now our specific volume is volume divided by mass. And while we should have looked for our H value, because when we found that this value for specific volume, right next to it there was value for enthalpy, which is all the energy it took to take it to that temperature and pressure from ice water. So we'll look that one up, but let's see what we got now. Now we've got, it went up to 0.6 cubic meters total volume, using a total volume or total mass of 0.3702, and we can get a new value for that. We have that one yet?
Yeah, 1.6207 meters cubed per kilogram.
Okay, so now go back to the tables. Remember that number, 1.6207, and what do we know? We know the new pressure is 250 kilopascals. Temperature is not known, but we know the specific volume. Oh, that's no fun. Let's find the H1 first. So H1 at 200 kilograms and 200 degrees C was a 2870. Third column's H. So it is, this is our beginning enthalpy. New value is at, oh. Okay, the ugly thing about this problem has a little CD disk that says EES, Engineering Equation Solver. They have these tables built into it, and it's like they don't have the 250 megapascals or 250 kilopascals on here. It's between these two. So we got we're at, we don't know where we're at. We could be anywhere around here, which is why you're asking the question. We had, you could do all sorts of, what you could do, if you were really enthusiastic about this, is split the difference between these two and take all these columns and say, average between these two and average all these until you found what you wanted, and then you come up to a temperature. If I average these two, 134 and 21 to 330, you get 1.65. And we're looking for 1.62. And yeah, we have to do like a four-way interpolation. My bad. I think for purposes of standing up here right now, I'm going to just say that the new number is 0.3 or 300 kilopascals, because we don't have those tables. I mean, you could do all this interpolation stuff. They want you to use, I didn't realize when they signed the problem that it wasn't in the table.
How do you do?
So we'll do it with numbers we have on the table here. And we'll take it up to 300.
Well, I know how to solve everything else. I just couldn't figure out how to get to the temperature using the.
To interpolate.
Yeah.
We'll do that with this one. So we'll say what do we know? The number is 1.62. And we're going to get different numbers than their answer because we just changed the pressure. So it's between these two. And this is sort of an interpolation example. 1.62, so we're between 700 and 800 degrees now because the pressure went up. We still, the specific volume is the same. We still have the same amount of mass, we still have the same size. So 1.4958, and for a specific volume, 1.65004. Oh, all right. Has anyone tried the CD in the back of the book? Used this for the homework or anything? There's not, that's like computers don't even take, my computer doesn't even take a CD anymore. Sort of like, you know, anyone use the cassette deck? You know, the original computers actually used, does anyone know what a cassette is? I remember the hot computer and the personal computer they had when I first, it was like was it Commodore 64? And it had a cassette tape that you would put your program on, and you'd wait like 5 minutes for it to go and load the program, one dot and dash at a time. It was like doing Morse code or something. Yeah, they actually used cassette decks for this is like information you don't need to know, right? I mean, okay, I get it. So the question is, what is my temperature here? So T, the temperature, we're assuming again this is the equal triangles kind of thing. So 700 degrees plus 100 degrees is the amount between, and then what's the proportion between 1.6207 is what we calculated. That didn't change. And all of these units cancel because they're all specific volume. And for those of you who have happy fingers, I want to know what this proportion is, because I'm going to use it with H.
I got 780 degrees.
And what did you get for the parentheses there? Probably 80.8, right?
Oh, I just did all once we calculator.
Okay. Did you get 780 exactly?
I got 80.97. So maybe like 780.
So since this is times 100, I can pretty much figure out that value was 0.80977. Does that make sense? So that means that my H final going to be H low plus the delta H, which I don't know what that is. It's not 100. My H values were 39, 28, 0.2, and 41, 59.3. And it'll have the same proportion there. So 39, 28.2 plus the difference, and these are kilojoules per kilogram. So what's that give us? Anyone run the numbers on that one? Forty-one, 15.34. I'm going to leave it at 0.3. That's the precision we have. So now we have a bunch of information. The total heat added will be mass times H2 minus H1, and we calculated the mass at 0.3702 kilograms. We've got two H values for the two different states that we cheated on, but by golly, we got them. 4115.3 minus the low one was 2870.7 kilojoules per kilogram, which is going to give us a total energy is that just the difference, or is that the total?
Oh, that was the difference.
Okay. That's the heat that would add to increase the temperature and cause the work to happen. Did something move to get bigger? Piston moved, right, from a certain size to another size. There was a spring holding it down. What do we know? We know the pressure changed. We know that it's a linear spring. Don't know the K factor for the spring. Don't know the area of the piston, but they gave us volume, so we're going to use that. They asked about a chart. And if we have pressure, and did we get a number on this one yet? 46075?
0.75.
Yeah.
0.75.
And that is in kilojoules, because this was kilograms and they cancel. That's the total amount of energy. You could turn that into so many pounds of fuel. And now the question, how much work was done? So pressure 1 was 200 kilopascals. Pressure 2 was cheated. We went to 300. And this was 0.4 meters cubed per kilogram. And this was 0.6. Oh no, that's just plain old volume. No per kilogram. Started off at 0.4. It got half again bigger. And since it was a linear spring, we know that the process went like that. It wasn't constant temperature, it wasn't constant pressure, wasn't a bunch of stuff. But what we know is this pressure, whatever that, the height of that is, times the change in volume, work is, a little bit of work is some value of pressure times change in, well, change in volume. You can either use this with capital letters or small letters. Capital letter would be total, small letters would be per kilogram. And if we add these all up, what it's telling me is that add them all up, that adds up all this area under here. It had to use this much pressure times that much distance. This is the work done. So do we need to make a calculus formula to solve this problem? It looks a lot like, well, the same as if we took, it would be the same area as a rectangle that's kind of has a height of the midpoint there, right? Just geometrically looking at it. Because it's a straight line, we can take an average pressure and say the work done is 250 kilopascals. Times delta 0.6 minus 0.4 meters cubed. Now, how is that going to get us work? So we got 0.2 times 250. I think that's going to be 50. According to my lightning fast supercomputer brain, which sometimes does have bugs in it. So if somebody comes up with a different number, let me know. Kilopascal times meters cubed, but 1 kilopascal is 1 kilonewton per meter squared. So we end up with 50 kilonewton meters. Anyone have another idea what we could call a Newton meter? Force times distance, it's unit of energy. Is that a kilojoule? And according to this, this is the work that was done. Our other number was the total amount of energy not only did the work get done, but the pressure was raised and the temperature was raised. And so out of all that, what we could say is that's the change in enthalpy total. This was the change in the work that was done total. So 50 of the 460 was work, and 410.75 was probably internal energy. The molecules are going faster, and the temperature increased and caused the pressure to increase, and that's all related. So that's how that would work. If you don't like, I didn't realize that problem didn't have the tables. I haven't encouraged you to use the disk because it gets too much. Like you rely on a crutch and you don't know how it works, and you don't really know. But once you understand tables well enough, then you can use that software. That's fine. And they're trying to get you to use it. I myself have never actually opened that software because we got enough trouble learning tables. But this is the process you go through. They wanted you to put out a pressure volume graph so you could see if it's a linear spring, this is going to be linear. If it was a nonlinear spring, this would have more of a scoop to it, and you need to know more information in order to get the curve of that line. It would make a difference if this line had a scoop that way or a scoop that way. The area under here is work, pressure times volume. So any questions on that other than I just changed the problem to suit myself? So we got an interpolation thing in there. If you used the software, it would already dial in your whatever values you wanted. So that being the case, I've also heard that some people were concerned about what might possibly be on the test that's coming up on Thursday. Is anyone curious about that? Show of hands. That's most everybody. Okay, for the rest of you, you'll just have to bear with us. And, you know, I find that I don't like giving tests. I'd rather be telling you more stuff, but it seems like if you aren't studying for a test, you don't really, it helps focus the mind, right, on topics. So I don't try and do tricks. It's going to be, you know, asking basic questions, hopefully. Yeah. So we have one question that's going to be property table. And, you know, there's pressure and there's temperature, enthalpy, specific volume, state. I don't know if I have all 5 categories in the table or if there's, I think it was just, I'm remembering 4 columns, but you know, there's 4 or 5 things to figure out. I'll give you this and this, or that and that, or this and some other random one. Any 2 things. Maybe it's something like that. Give you 2 things and fill out the rest of them. Figure out, are you in superheat? Are you saturated? Are you below saturation? Super cooled or super compressed or whatever. For liquid below saturation, unsaturated, I guess would be the best way to call it, but they call it supercooled if you're talking about temperature, or compressed if you're talking about pressure relative to saturation. And then, so that's what the state is about. Is it in saturation or not? And then there's sort of a related one. I give you mass, give you a volume, give you a pressure. Find specific volume, quality, and total enthalpy. I've made a big H. Half the papers will come back with small h, because if you know what the mass is and you know what the volume, that gets you the specific volume pretty fast. If it's in saturation, it's I should say, liquid vapor mix. You won't get a quality number if it isn't. That's actually one of the things you can look at. If you get a specific volume when you do a calculation and you look at the pressure and it's not in that saturation zone, then it's because it's not a liquid volume, it's going to be superheat or it's going to be a liquid. It's out of that zone. You're not going to have a quality. The quality just says what is the mass percent that's a vapor. And you use this to find that, you use that to find this. And then there's another, two more problems, and these ones are more sort of fluid related. It's about power and work, and this may not be so much in the book, or harder to find in the book, but and it's related to hydropower and efficiencies and such. It's so if work, we just did this, a fixed amount of work, I pushed it so far and I did some work. The power is how fast did you do it. If you got low power, it goes slow. If you got high power, it goes fast, but you do the same amount of work. But work was defined as pressure times the change in total volume. Specific work per unit something would be still big pressure and change in specific volume. Power equals how fast, work per unit time. How would that, and I think for the purposes of this hydro thing, it's about total volume. We're not talking small volume. We're not so much scaling it up. But power times the change in volume. How do we make that happen here? We got power, or power is pressure times change in volume. What do we do with the time over some amount of time? dV dt, change in volume with time. What is change in volume with time? It's a rate, so it would be like gallons per minute, cubic meters per second, liters per hour. So if you have a pressure and you have a volume flow rate, that generates fluid power. Now, if we're talking about a fluid with this much pressure and this much flow rate, that's the fluid, that's the power in the fluid. What if the turbine can't capture it all? And they don't. They can't capture it all. For example, well, no, I won't get there. But basically, you have to have some kinetic energy for the fluid. If you had all turn all the potential energy into the turbine extracted it all, it wouldn't have enough energy to get out of its own way, right? There's no kinetic energy left, so it just stays at the bottom of the turbine, which blocks the rest of it. So you can't use all of the water or energy, all the energy from the water, because it can't literally get out of its own way. So you have to leave some energy for it to leave. So it's never going to be 100% efficient in converting the potential energy. And pressure is potential energy, basically. It actually has units of kilojoules per cubic meter, if you think about it. So efficiency of a turbine. Actually, I'll move that over here where we've got this other stuff going on. So part one is what's the power in the water, and part two is if the turbine is a certain amount efficient, what's the turbine output that you could expect? And how we define power of the turbine, it's work done or the power, actual output divided by, that's what you got is the actual output. What did you put into it? What went in? What did it cost you? Is water, the power that was in the water, which is this one. So if the first question is how much power is in the water, the second question would be if your turbine is this efficient, what's the shaft power output? So if I give you this, and I give you this, you should be able to come up with that. And another topic. Oh, and by the way, part of well, both of these are kind of, this one's not only fluids, it's also some thermal things in here. This one's more about fluids. Density times gravity times height is our basic pressure. A change in pressure would be rho g change in height. And in this case, I should actually change the problem. One part of it is calculating this, which is not, on this one I give you a pressure, this one I ask you to calculate one, and then it seems like I do another, with a certain volume flow rate, what kind of power are we getting out of it. So it's like a recalculating this thing. In case you didn't get it here, you'll miss it here too. Or it's a gift. If we can make this work, then that one's a piece of cake. But so I'm going to give you H don't recall if I gave you a density on here, but be aware things matter. What temperatures are, temperatures for a liquid will give it a different volume, a different density. So, you know, if you can't figure out, I don't necessarily put in extra information, but sometimes I do, just inadvertently. But if there's a specific temperature mentioned, don't just say, oh, water's 1,000. I mean, I do that a lot. I'll say water's 1,000, you know, kilo whatever's. And most of the time, if you do that, you're off by 0.2% or something, 0.5%. But if I give it to you and I want that data, I want to see that you got that data, that's one of your things that I'm looking for. Also units, make sure you're following your units and you put units down because they give meaning to the numbers. That's what the test is about. All right, that must be time. See you tomorrow.